Hello, and welcome to Sleepy Story World. Tonight, we are going to spend 2 hours asking one of the most unsettling questions in all of human exploration. What actually happens to a human being in deep space? Not in science fiction, not in a film where the hero floats dramatically and survives. In documented, measured, physically confirmed reality. The radiation that passes through walls as though they are not there. The vacuum that kills in under 2 minutes. The distance that makes every problem unsolvable. And the slow, quiet way that deep space dismantles a human body and a human mind simultaneously. Without drama, without mercy, and without pause. In April 2026, 4 astronauts flew around the Moon aboard NASA's Orion spacecraft. 10 days, a minivan-sized capsule, a few centimeters of aluminum between them and the void. NASA called radiation the #1 showstopper for deep space exploration. And that 10-day flight barely scratched the surface of what a real deep space mission would require. Because beyond the Moon, beyond Mars, beyond every destination humans have ever seriously discussed, there is a region so hostile that every layer of protection we have ever built begins to fail simultaneously. Not in one dramatic explosion, through a slow, total collapse of every condition your body requires to exist. Find a comfortable position. Let your breathing slow. There is no rush where we are going tonight. Let's begin. Close your eyes and picture an astronaut. You probably see someone in a white suit floating inside a gleaming module. Sunlight streaming through a cupola window. Earth curving blue and enormous just below. Maybe they are conducting an experiment, squeezing a blob of water in microgravity, or waving at a camera while a wrench tumbles in slow motion nearby. The image feels dangerous but contained, risky but managed, like rock climbing with a good harness, like scuba diving with a reliable tank. The astronaut is in space, sure, but they seem fine. They seem like they are handling it. This image is the most dangerous lie in human spaceflight. Not because it is fabricated. Everything you picture is real. Astronauts genuinely do float inside modules, conduct experiments, and gaze at Earth through the windows of the International Space Station. The lie is not in what you see. The lie is in what that image teaches your brain about what being in space actually means. Because the International Space Station is not in deep space. It is not even close. And the difference between where the station flies and where deep space begins is not a matter of degree. It is a difference so fundamental that it changes the entire nature of survival. It changes what the word survival even means. The International Space Station orbits Earth at roughly 400 kilometers altitude. That is approximately 250 miles. The distance from New York City to Washington, D.C. is about 360 kilometers. The station is closer to the surface of Earth than those 2 cities are to each other. If you could drive straight upward at highway speed, you would reach the station's altitude in under 4 hours. This is not a remote outpost at the edge of the solar system. This is a laboratory skimming along the uppermost layer of Earth's atmosphere, orbiting so close that it circles the entire planet every 90 minutes. When something goes wrong on the station, and things go wrong regularly, the crew can climb into a Soyuz or Crew Dragon capsule and be back on the ground within hours. Resupply ships arrive within days. Communication with Mission Control in Houston is nearly instantaneous. If a medical emergency strikes, if a fire breaks out, if the oxygen generation system fails, there are protocols, backups, and an escape hatch that leads to the safest planet in the known universe in less time than it takes to watch a long movie. This is not deep space survival. This is supervised camping on your own front lawn. Now consider what lies beyond that comfortable orbit. Above the station, extending outward from Earth in a vast, invisible architecture, sits the magnetosphere. This is Earth's magnetic field, inflated into a colossal bubble by the pressure of its interaction with the solar wind, stretching tens of thousands of kilometers into space on the day side and millions of kilometers on the night side, in a long, trailing tail. The magnetosphere is the single most important reason you are alive right now, and you have never once perceived it with any of your senses. It is invisible, silent, odorless, and intangible. But without it, the surface of Earth would be scoured by charged particles streaming from the sun at over 1,000,000 miles per hour. The atmosphere would be slowly stripped away, the way it was stripped from Mars billions of years ago, when Mars lost its global magnetic field. Life as we know it would never have gained a foothold. Inside the magnetosphere sits another layer of protection most people never think about. The Van Allen radiation belts, two concentric donut-shaped zones of trapped charged particles, primarily protons and electrons, caught in Earth's magnetic field lines. The inner belt extends from roughly 1,000 to 12,000 kilometers above the surface. The outer belt stretches from approximately 13,000 to 60,000 kilometers out. These belts are not gentle. The radiation inside them is intense enough to damage satellites and degrade solar panels. Apollo astronauts passed through them quickly during their lunar transits, spending only about 30 minutes in the most dangerous regions. But here is the critical point. The International Space Station orbits well below the inner Van Allen belt. It flies beneath the densest regions of trapped radiation, tucked inside the magnetosphere like a bird under a cathedral ceiling. The station receives some radiation, roughly 0.5 millisievert per day, compared to about 0.01 millisievert per day on Earth's surface. That is elevated. It is a real occupational hazard, but it is a managed hazard because the magnetosphere is still doing most of the heavy lifting. Now imagine crossing that boundary. Imagine leaving the magnetosphere entirely. Beyond the Van Allen belts, beyond the outermost reach of Earth's magnetic influence, the environment changes so drastically that using the same word, space, for both locations is almost misleading. Out there, the magnetic shielding vanishes. The charged particles that Earth's field had been deflecting for billions of years now have a clear path to your spacecraft, your suit, and your body. Galactic cosmic rays, ancient particles accelerated by supernovae and other cataclysmic events across the galaxy, arrive from every direction with energy so extreme that a single subatomic particle can carry more momentum than its size has any right to possess. There is no magnetic field to bend their paths. There is no atmosphere to slow them down. There is no ozone layer to filter anything. There is just the hull of your spacecraft. And as we will spend this evening discovering, that hull is not nearly enough. This is what deep space means in the context of tonight's story. Not the region just above Earth's atmosphere where the station flies. Not the brief transit zone through the Van Allen belts that Apollo astronauts crossed in under an hour. Deep space means the interplanetary medium and beyond. The vast emptiness between worlds, where no planetary magnetosphere offers shelter, where no atmosphere absorbs incoming energy, where no surface provides shielding from below, and where the nearest rescue is not hours away, but months or years away, if rescue is possible at all. And this distinction matters more than almost anything else in the conversation about human survival in space. It is a distinction that popular culture almost never makes. When you watch a science fiction film set on a spacecraft traveling between planets, the interior usually looks like a submarine with better lighting. Crew members walk through corridors, eat meals at tables, sleep in bunks. Between the dramatic moments, the crew seems comfortable, safe. The ship appears to handle space the way a well-built house handles winter. Your brain absorbs this framing without questioning it, because the framing matches your intuition. We handle cold and empty environments on Earth all the time. We build research stations in Antarctica. We send submarines to crushing depths. We construct habitats in deserts. In every case, the solution is engineering. Build a better shelter. Carry more supplies. Design redundant systems. The instinct is to assume that deep space survival is just the next step on that ladder. It is not. Every hostile environment on Earth shares one crucial feature that deep space does not: a background of survivability. In Antarctica, if your heating system fails, the air outside is brutally cold. But it is still air. You can breathe it. If your shelter collapses, you can build a snow cave. The environment is trying to kill you through cold, but it is only trying to kill you through cold. The atmosphere is still there. Gravity is still there. Pressure is still there. Oxygen is still there. Rescue is still possible. Deep space offers none of this. In deep space, if your life support fails, there is no air outside the hull. There is no air anywhere within millions of kilometers. If your heating system breaks, the background temperature of space is approximately 2.7 Kelvin, roughly minus 270 degrees Celsius, just a few degrees above absolute zero. If your pressure hull cracks, the air inside does not leak slowly like air escaping a tire. In hard vacuum, the pressure differential is absolute. You lose consciousness in roughly 10 to 15 seconds. Death follows within minutes. And if your navigation or propulsion fails, there is no pulling over, no coasting to harbor. You are moving through a void where the nearest solid surface might be tens of millions of kilometers away, and reaching it requires precise orbital mechanics that cannot be performed without functioning computers and functioning engines. This is the reality that the comfortable image of the space station conceals. The station is a marvel of engineering, but it survives because of where it is, not only because of what it is. Remove the proximity to Earth, remove the magnetic shielding, the rapid communication, the emergency return capability, the regular resupply, and the station itself would become a death trap within months. Deep space has no extension cord. There is a particle racing toward you right now. It began its journey millions of years ago, launched from the shockwave of a dying star somewhere across the galaxy. It is a single iron nucleus, stripped of all its electrons, accelerated to within a fraction of a percent of the speed of light by forces so violent that nothing in our solar system can replicate them. This particle is smaller than an atom, invisible to every instrument on your body, and it carries the kinetic energy of a baseball thrown by a professional pitcher. All of that energy concentrated into a space smaller than a trillionth of a millimeter. Right now, Earth's magnetosphere is bending this particle's trajectory so that it spirals harmlessly past the planet and continues into the void. You will never know it existed. An astronaut in deep space does not have that luxury. That particle, or one of the billions like it streaming through interplanetary space at every moment, would pass through the wall of a spacecraft, as though the wall were not there. It would enter the astronaut's body and carve a microscopic trail of destruction through every cell in its path, breaking molecular bonds, shattering DNA strands, ionizing atoms, and leaving behind a column of damaged tissue, thinner than a human hair, but biologically devastating. Scientists call these particles galactic cosmic rays, and they represent perhaps the single most intractable problem in human deep space exploration. Galactic cosmic rays are not what most people imagine when they hear the word radiation. They are not the gentle warmth of sunlight. They are not the X-rays from a medical scan. They are atomic nuclei, some as heavy as iron or heavier, accelerated to energies that dwarf anything produced by particle accelerators on Earth. They originate from supernovae, from the violent deaths of massive stars, from the energetic cores of distant galaxies, and from sources astronomers have not yet fully identified. They arrive from every direction in roughly equal intensity, meaning there is no way to orient a spacecraft to avoid them. They do not come in bursts or waves. They come constantly, a steady rain of subatomic shrapnel that never stops, day or night, year after year, for the entire duration of a mission. On Earth, you receive a radiation dose of roughly 2 to 3 millisieverts per year from all natural background sources combined. An astronaut aboard the International Space Station receives roughly 150 to 200 millisieverts per year. Elevated but manageable, because the magnetosphere still blocks most galactic cosmic rays at the station's altitude. In interplanetary space beyond the magnetosphere, the dose approximately triples. NASA's measurements, confirmed by instruments aboard the Curiosity rover during its transit to Mars in 2011 and 2012, recorded an average dose rate of roughly 1.8 millisieverts per day in interplanetary space. Multiply that by the approximately 360 days of a minimum duration Mars transit round trip, and the crew accumulates over 650 millisieverts from galactic cosmic rays alone, before accounting for any additional radiation from solar events or surface exposure. That figure exceeds the entire career radiation exposure limit NASA currently sets for its astronauts, and that is from galactic cosmic rays alone, before a single solar storm. Now, here's the part that should unsettle you more than any other detail in this entire story. We do not know how to stop them. The intuitive solution is shielding, build thicker walls, add more material between the crew and the incoming particles. And for lower energy radiation, solar ultraviolet, X-rays, and even the protons from moderate solar particle events, this works. But galactic cosmic rays are different. Their energies are so extreme that they do not simply stop when they hit a wall. Instead, the incoming heavy ion collides with the nuclei of atoms in the shielding material and shatters them. The collision produces a spray of secondary particles, lighter fragments, neutrons, protons, and other subatomic debris that scatter forward into the spacecraft interior. These secondary particles are themselves biologically damaging. Some are actually more dangerous per unit of energy than the original cosmic ray, because neutrons deliver their energy to tissue in ways that cause disproportionate biological harm. This creates a problem that sounds almost paradoxical. Adding more shielding material can increase the crew's total radiation dose rather than decrease it. Research published in the journal Space Weather confirmed through simulation that increasing aluminum shielding past roughly 20 to 30 grams per square centimeter begins to produce a net increase in effective dose to blood-forming organs. Because the secondary radiation generated inside the thickened wall outweighs the primary radiation it manages to stop. You reach a point of diminishing returns and then cross into a regime where more protection makes things worse. There are materials that perform better than aluminum. Hydrogen-rich compounds like polyethylene and water are more effective because hydrogen nuclei are similar in mass to incoming protons, absorbing energy more efficiently without producing as many heavy secondary fragments. NASA has investigated using water tanks and polyethylene blocks strategically placed around crew quarters. But even these superior materials cannot eliminate galactic cosmic ray exposure. They reduce it. They do not solve it. The mass required to bring galactic cosmic ray doses down to Earth's surface levels would make the spacecraft too heavy to launch with any propulsion technology that currently exists. One estimate calculated that reducing exposure to permissible levels through passive shielding alone during a 500-day Mars mission would require approximately 1,280 metric tons of material, the equivalent of 32 heavy-lift rocket launches just for the radiation shielding. That number is not a design challenge. It is a physical impossibility within any realistic mission architecture. Active shielding, using powerful magnetic or electrostatic fields generated by onboard systems to deflect incoming charged particles, has been proposed as an alternative. The concept is elegant. Replicate what Earth's magnetosphere does, but around a spacecraft. In practice, the engineering obstacles remain enormous. The magnetic fields required would need to be extraordinarily strong and sustained over large volumes, demanding superconducting magnets, cryogenic cooling systems, and power generation far beyond what any crewed spacecraft has ever carried. As of 2026, no active shielding system has been tested in space at a scale relevant to crew protection. So the galactic cosmic ray problem sits there, unresolved, constant, and implacable. Every second of every minute of every hour that an astronaut spends beyond the magnetosphere, heavy ions are passing through their body, breaking DNA, damaging cells, and accumulating biological harm that compounds over time. The effects are not immediate, they are insidious. The galactic cosmic ray exposure increases the lifetime risk of cancer, accelerates the onset of cardiovascular disease, damages the central nervous system in ways that may impair cognition and memory, and promotes the formation of cataracts. None of these announce themselves during the mission. They manifest months or years after return, written into the astronaut's biology by particles they never saw and never felt. But galactic cosmic rays are only the chronic background. Layered on top of them is the acute danger: solar particle events. The Sun is not a steady, well-behaved star. It is a churning nuclear furnace with a magnetic field that periodically tangles, snaps, and releases staggering amounts of energy in events called solar flares and coronal mass ejections. When these eruptions are directed toward a spacecraft in interplanetary space, they deliver a wave of energetic particles, primarily protons, that can arrive within minutes to hours. On August 4th, 1972, one of the most powerful solar particle events of the modern era erupted from the Sun. Had an Apollo crew been in transit to or from the Moon during the peak of this event, they would have been exposed to estimated doses exceeding 1,000 millisieverts within hours. At that level, acute radiation sickness sets in rapidly. Nausea, vomiting, diarrhea, fatigue, and immunosuppression are the early symptoms. At higher doses, damage extends to bone marrow, the gastrointestinal lining, and the central nervous system. Without medical intervention, doses above 3,000 millisieverts become lethal within days to weeks. The August 1972 event fell between the Apollo 16 mission, which returned in April, and the Apollo 17 mission, which launched in December. The timing was pure luck. Solar particle events cannot be predicted with more than a few hours of warning, sometimes less. A deep space crew would need to retreat to the most heavily shielded section of the spacecraft whenever a warning is issued, and remain there for hours or even days. For a 9-month Mars transit, adequate protection becomes a matter of sustained luck. And if the event is large enough, even the storm shelter may not reduce the dose to safe levels. Radiation then presents a double bind. The chronic threat cannot be blocked. The acute threat can be partially mitigated, but never eliminated. And both threats interact with the body's repair mechanisms in ways that are worse in combination than either would be alone. The immune system already stressed by microgravity and confinement, is further compromised by radiation damage to bone marrow. The very cells responsible for identifying and destroying precancerous mutations are themselves degraded by the radiation that creates those mutations. The body is being damaged faster, while its repair systems are being weakened. Consider what the vacuum of space actually does to a human being. Not in science fiction, not in metaphor. In documented, observed, experimentally confirmed physical reality. In 1966, a technician at NASA's Manned Spacecraft Center in Houston was testing a spacesuit in a vacuum chamber when the suit suffered a rapid decompression. The pressure dropped to mere vacuum within seconds. The last thing the technician reported feeling before losing consciousness was the sensation of saliva boiling on his tongue. He was repressurized within approximately 15 seconds and survived with no permanent injury. But the event provided one of the few direct human data points for vacuum exposure. And what it revealed was consistent with decades of animal research. When a human body is suddenly exposed to hard vacuum, the sequence of physiological collapse follows a precise and merciless timeline. Within the first second, air in the lungs begins rushing outward through the airway. If the person holds their breath, the expanding gas can rupture the alveoli, the tiny air sacs in the lungs, causing potentially fatal barotrauma. The correct survival response, counterintuitively, is to exhale and let the air go. Within 5 to 10 seconds, dissolved gases in the bloodstream begin coming out of solution, forming bubbles in the tissues and circulatory system. This is ebullism. Water in the skin and mucous membranes begins transitioning to vapor at body temperature, because the boiling point of water drops below 37 degrees Celsius when ambient pressure falls sufficiently low. The body swells, dramatically and painfully, though it does not explode. Human skin and connective tissue are strong enough to contain the expanding vapor. Consciousness is lost within 10 to 15 seconds, as the partial pressure of oxygen in the blood drops below the threshold needed to sustain brain function. The heart continues beating for a short time, but without oxygen, the brain begins suffering irreversible damage within 3 to 4 minutes. If the person is repressurized within roughly 60 to 90 seconds, survival is possible. Beyond that window, the damage becomes unsurvivable. Note what this timeline means for a deep space crew. The margin between a survivable pressure loss and a fatal one is measured in seconds. A micrometeorite puncture, a seal failure, a structural crack caused by thermal cycling or material fatigue. Any breach in the pressure hull starts a clock that gives the crew less than 2 minutes to identify the leak, isolate the affected section, and restore pressure. In a small spacecraft with limited volume and limited spare atmosphere, even a slow leak that is not immediately detected could reduce cabin pressure to dangerous levels during a sleep period when no one is monitoring instruments. And unlike on the International Space Station, where a leak can be addressed with resupply from Earth, a deep space crew has only the atmosphere they launched with. Every molecule of oxygen and nitrogen aboard is irreplaceable. The threat of hull breach is not theoretical. Interplanetary space is threaded with micrometeoroids, tiny fragments of cometary and asteroidal debris ranging in size from grains of dust to small pebbles, all of them traveling at velocities between 10 and 70 kilometers per second. At those speeds, a particle smaller than a grain of sand carries enough kinetic energy to puncture spacecraft shielding. A particle the size of a pea strikes with the force of a hand grenade. The kinetic energy scales with the square of velocity, and at 40 kilometers per second, even a particle weighing a fraction of a gram delivers energy equivalent to a rifle bullet. Unlike in low Earth orbit, where the population of orbital debris is tracked by ground-based radar and spacecraft can be maneuvered to avoid known objects, micrometeoroids in interplanetary space are untrackable. They are too small, too numerous, and too fast to detect before impact. No radar network monitors the transit corridor between Earth and Mars. The crew simply flies through this environment and trusts the hull's Whipple shielding, a multi-layered bumper system designed to vaporize incoming particles before they reach the pressure wall. Whipple shields work well against the most common particle sizes, but they have limits. A sufficiently large or dense particle can defeat the shielding, and on a 900-day mission, the cumulative probability of encountering a particle large enough to defeat the shielding is not negligible. It is a statistical risk that grows with every day of exposure. This dependency on the pressure hull transforms the spacecraft from a vehicle into something more fundamental. The crew does not merely ride inside the hull. They are existentially dependent on it in a way that has no parallel in any other human experience. A submarine depends on the hull to keep water out. But if the hull was somehow removed, the submarine would still be surrounded by a medium that contains dissolved oxygen, that exerts survivable pressure at shallow depths, that supports swimming and breathing at the surface. Remove the hull of a deep space spacecraft, and the crew faces the absolute vacuum of interplanetary space. There is no surface to swim toward. There is no medium to breathe. There is no pressure to sustain consciousness. There is nothing. The hull is not a convenience. It is the boundary between existence and annihilation, and it must hold for years without inspection from the outside, without repair crews, and without the option of pulling into a maintenance facility. Then there is the thermal environment, which operates on a logic that defies everyday human experience. On Earth, you understand temperature intuitively. Cold air chills you. Warm sunlight heats you. You move between heated buildings and cold streets, and your body manages the transitions through clothing, circulation, and metabolic heat generation. All of this works because you live in a medium, air, that conducts and convects heat. In the vacuum of deep space, two of the three mechanisms for heat transfer vanish entirely. There is no air, so there is no conduction to a surrounding medium, and no convection currents to carry heat away. The only remaining mechanism is radiation, the emission and absorption of infrared photons. A spacecraft in deep space that faces the sun absorbs solar radiation on its sunward surface. Near Earth's orbit, the solar flux is approximately 1,367 watts per square meter, enough to heat an unshielded surface to well over 100 degrees Celsius. But the opposite side of the spacecraft, facing away from the sun, radiates heat into the cosmic background at minus 270 degrees Celsius. Without insulation, that shadowed surface could cool to -150 degrees or colder. The temperature difference between the sunlit and shadowed sides of the same spacecraft can exceed 250 degrees. On a rotating spacecraft, surfaces cycle between these extremes every few minutes. These thermal swings stress every material in the spacecraft. Metals expand and contract. Seals flex and fatigue. Adhesives soften in heat and become brittle in cold. Solar panels, radiators, antennas, and external instruments undergo thousands of thermal cycles over a multi-year mission, each cycle pushing the materials a little closer to failure. Thermal failure is a creeping threat. It begins as an anomalous sensor reading and ends days or weeks later as a cascading systems crisis. And it cannot be repaired from outside, consulted on in real time, or addressed by anyone who is not already sealed inside the spacecraft with the crew. Microgravity is not a hazard in the conventional sense. It does not injure you. It does not burn, irradiate, or suffocate you. It simply removes the constant downward pull that every system in your body was designed by evolution to operate under. And in the absence of that pull, the body begins, quietly, methodically, invisibly, to dismantle itself. The process starts within hours of reaching weightlessness. Without gravity pulling blood toward the feet, body fluids redistribute upward, pooling in the chest and head. The face puffs, the legs thin. The heart, sensing what it interprets as excess fluid volume, triggers hormonal signals to reduce blood plasma. Within days, astronauts lose roughly 10 to 15% of their circulating blood volume. The heart, no longer needing to pump blood uphill against gravity, begins to atrophy. Studies of long-duration station crew members have documented measurable decreases in cardiac muscle mass after just 6 months. The heart does not just weaken. It changes shape, becoming more spherical as the load it was designed to bear disappears. Bone loss is even more alarming. On Earth, your skeleton constantly remodels itself under mechanical stress. Osteoblasts build new bone where load-bearing demands it. Osteoclasts remove bone where it is no longer needed. Gravity provides the baseline load. Without it, the body concludes that the skeleton is overbuilt and begins dismantling it. Astronauts on the International Space Station lose roughly 1 to 1.5% of their bone mineral density per month in weight-bearing bones like the pelvis, spine, and femur. Over a 9-month Mars transit, that translates to 9 to 13% bone loss, approaching the threshold at which fracture risk becomes clinically significant. On Earth, this rate of bone loss would take a decade of severe osteoporosis to match. In space, it happens in months, and the calcium stripped from the bones does not vanish. It enters the bloodstream and must be excreted by the kidneys, increasing the risk of kidney stones, a condition that on Earth is agonizingly painful but treatable, and in deep space could be medically incapacitating with no surgical recourse. Muscles atrophy at comparable rates. Without the constant resistance of gravity, the large postural muscles of the legs and back lose mass and strength at roughly 3 to 5% per month, despite mandatory exercise regimens. Astronauts returning from 6-month station missions often cannot stand unassisted for the first hours after landing. After a Mars transit, the crew would arrive at a planet with roughly 38% of Earth's gravity, in a state of physical deconditioning so severe that simply walking on the surface would pose a real risk of falls and fractures, precisely because the bones and muscles that should support them have been quietly consumed by the weightlessness of the journey. Perhaps most troubling is what microgravity does to the brain. The upward fluid shift that begins on the first day of weightlessness increases intracranial pressure. Over weeks and months, this sustained pressure pushes on the back of the eyeballs, flattening them and distorting vision. The condition is formally called spaceflight-associated neuroocular syndrome, and it has been documented in a significant percentage of long-duration astronauts. Some return to Earth with measurable structural changes to their optic nerves and retinas. Some experience lasting changes to their visual acuity. In a deep space scenario, worsening vision during the mission could impair the crew's ability to read instruments, perform repairs, or pilot the spacecraft during critical phases. And there is no ophthalmologist aboard. There is no corrective surgery available. There is only the slow, steady pressure of fluid on structures that evolved to function under gravity's downward pull. Now subjected to a continuous upward displacement, the body has no mechanism to correct. The vestibular system, the inner ear apparatus that provides you sense of balance and spatial orientation, suffers its own form of confusion. On Earth, tiny crystals called otoliths shift under gravity's pull to tell your brain which way is down. In microgravity, down ceases to exist. The otoliths float. The signals they send become meaningless. Space motion sickness affects roughly 60 to 80% of astronauts in the first days of weightlessness. The brain eventually adapts, but this adaptation is itself a form of deconditioning. When the crew arrives at Mars and re-enters a gravitational field, the vestibular system must readapt over days to weeks. During that period, crew members experience dizziness, difficulty walking, and a heightened risk of falls. They arrive at the most critical phase of their mission in a state of neurovestibular dysfunction that would ground a pilot on Earth. The immune system presents perhaps the most insidious form of microgravity damage because it interacts directly with the radiation threat. Research on station crew members has documented measurable changes in immune function during spaceflight, including altered distribution of white blood cell populations, reduced activity of natural killer cells responsible for destroying virus-infected and precancerous cells, and reactivation of dormant viruses that the immune system normally keeps suppressed. These changes begin within the first weeks of spaceflight and persist throughout the mission. In a deep space environment, where radiation is simultaneously increasing the rate of DNA damage and the formation of potentially cancerous cells, an immune system that is less capable of identifying and destroying those cells represents a compounding vulnerability that neither hazard alone would produce. The body is being damaged faster while its repair systems are being weakened. Exercise helps. 2 hours of daily resistance and cardiovascular training on the International Space Station reduces but does not eliminate bone and muscle loss. But exercise equipment is heavy occupies precious volume, requires maintenance, and consumes crew time that competes with every other demand of the mission. And even the most rigorous regimen cannot replicate the constant omnidirectional loading that gravity provides every second of every day on Earth. Exercise is a partial countermeasure, not a solution. The body still degrades. It just degrades more slowly. And unlike radiation or vacuum, microgravity cannot be shielded against or contained behind a barrier. It is a property of the environment itself, acting on every cell of every crew member for every second of the mission. There is no room aboard the spacecraft where gravity exists. There is no hour of the day when bones stop dissolving. The deconditioning is total, constant, and cumulative, and it will not reverse until the crew returns to a gravitational environment. A return that is months or years away, and that will demand a body strong enough to survive atmospheric re-entry and landing. And this is the point that no hazard list can properly convey. These threats do not take turns. Radiation does not pause while the crew deals with a thermal anomaly. A pressure integrity concern does not wait until the solar particle event subsides. Microgravity does not stop degrading bone density while the crew troubleshoots a water recycling failure. Every single hazard in deep space operates simultaneously, continuously, and cumulatively. They interact with each other in ways that compound the danger beyond what any individual threat assessment can capture. Radiation degrades the materials that maintain pressure integrity. Thermal cycling weakens the seals that keep atmosphere inside the hull. The same micrometeorite that punctures an insulation blanket exposes the underlying structure to thermal extremes that accelerate material fatigue. The physiological stress of microgravity weakens the immune system, making the crew more vulnerable to the cancer-promoting effects of radiation. Radiation damages bone marrow, compounding the immune suppression that microgravity has already initiated. Sleep disruption caused by the artificial light cycle aboard the spacecraft reduces cognitive performance, making the crew less capable of responding to system failures that any of these other hazards might produce. Each problem feeds into the others. Each vulnerability exposes another vulnerability. The environment does not present one challenge at a time. It presents all challenges at once, constantly, with no breaks, no holidays, and no option to step outside and breathe fresh air while you think. Imagine you are standing in your kitchen and you smell smoke. You do not panic. You look around, find the source, maybe a towel too close to a burner, and you deal with it. You grab the towel, toss it in the sink, run water over it. Crisis resolved in 30 seconds. Now imagine the same scenario, but you are locked inside your kitchen. The door is welded shut. The windows are sealed. The fire extinguisher is in another room you cannot reach. Your phone has a 40-minute delay before anyone hears your call, and another 40 minutes before their response reaches you. And the nearest fire station is 8 months away by the fastest vehicle ever built. The towel is still burning, the smoke is still rising, and you are still standing there, alone, with only whatever happens to already be inside that room. This is what distance does to every problem in deep space. It does not merely make problems harder to solve. It changes the fundamental nature of what a problem is. Begin with communication, because communication is the thread that connects every other problem to its potential solution. On the International Space Station, communication with mission control is essentially continuous and essentially instantaneous. The signal delay is negligible, roughly half a second. When an alarm sounds on the station, the crew hears it at the same moment. Flight controllers in Houston see the telemetry. They can talk through the problem in real time. Controllers can pull up schematics, consult engineering teams, run simulations, and relay step-by-step guidance while the crew works the issue. This real-time loop has saved lives. During the carbon dioxide scrubber crisis on Apollo 13, the ground team in Houston worked the problem in parallel with the crew, devising a solution using materials known to be aboard the spacecraft and talking the astronauts through the improvised repair. That collaboration was possible because the communication delay between Earth and the Moon is only about 1.3 seconds each way. Conversation was slightly lagged, but functionally real-time. Now extend that delay to Mars. Depending on where Earth and Mars sit in their respective orbits, a one-way signal takes between roughly 4 minutes and 24 minutes. A round-trip exchange takes between 8 and 48 minutes. At maximum distance, when the Sun sits between the two planets, communication may be blocked entirely for weeks. Consider what this means in an emergency. An alarm sounds aboard the spacecraft. The crew sends a message to mission control. 8 minutes later, at minimum, the message arrives at Earth. Flight controllers assess the data, consult engineers, formulate a response. Even if they reply within 5 minutes, the crew does not hear back for another 8 minutes. 21 minutes have now passed since the alarm sounded. During those 21 minutes, the crew has been entirely on their own, making decisions with whatever information and training they possess, unable to consult the thousands of engineers and specialists who designed the systems they are trying to fix. And 21 minutes is the best case. At maximum orbital separation, the same exchange takes over 50 minutes. For certain categories of emergencies, 50 minutes is an eternity. A rapid cabin depressurization can render the crew unconscious within 15 seconds if the breach is large. A fire in a closed spacecraft environment can become unsurvivable within minutes as toxic combustion products fill the cabin. An acute medical emergency, a cardiac arrest, a traumatic injury, a severe allergic reaction, demands immediate intervention. In none of these scenarios can the crew afford to wait 8 minutes for guidance, let alone 50. They must act immediately, correctly, and with whatever resources are physically within reach. There is no calling for help. There is no second opinion. There is no ambulance coming. This transforms the crew from passengers supported by a global infrastructure of expertise into the sole operators of every system aboard their spacecraft. They are the mechanics, the electricians, the plumbers, the doctors, the pharmacists, the computer technicians, the structural engineers, and the crisis managers. every crew member must carry enough cross-training to troubleshoot systems far outside their primary specialty, because a failure does not care whether the available crew member is qualified to address it. If the life support specialist is asleep when the carbon dioxide scrubber fails, whoever is awake becomes the life support specialist for the next critical minutes. If the medical officer suffers the medical emergency, the remaining crew must provide treatment with whatever training they have received, which, no matter how extensive, cannot replicate decades of emergency medicine experience. The medical dimension of this isolation deserves particular attention, because it reveals the distance problem at its most visceral. On Earth, a medical emergency triggers a system. You call an ambulance. Paramedics arrive within minutes. A hospital with surgeons, imaging equipment, blood banks, pharmacies, and intensive care units receives you within the hour. The system is so deeply embedded in modern life that we rarely think about how many specialized professionals and how much infrastructure stand behind the phrase, "call a doctor." A deep space crew has none of this. They have a medical kit. They have a limited pharmacy that cannot be restocked. They have diagnostic equipment constrained by mass and volume limitations. And they have crew members trained in emergency medical procedures to a level that, while impressive, cannot replicate the capabilities of a trauma center. Consider appendicitis, one of the most common surgical emergencies in human medicine, occurring in roughly 7% of the population over a lifetime. On Earth, it is treated with a straightforward appendectomy, and the patient typically recovers within weeks. On a deep space mission, appendicitis becomes a potential mission-ending event. Performing abdominal surgery in microgravity inside a spacecraft with no anesthesiologist, no sterile operating theater, no blood transfusion capability, and no possibility of post-operative intensive care introduces risks that would be considered unacceptable in any terrestrial medical context. Blood does not pool predictably in microgravity. It floats. Incisions release globules of blood that drift through the cabin air, creating both a contamination hazard and a visibility problem for the surgeon. Post-operative infection, which on Earth is managed with intravenous antibiotics, monitoring, and potential reoperation, becomes a critical threat when the antibiotic supply is finite, and there is no possibility of reoperation if the first attempt fails. The pharmacy problem alone is sobering. Medications degrade over time, and they degrade faster in the radiation environment of deep space. Studies have shown that the potency of many common pharmaceuticals decreases measurably after 6 to 12 months of storage aboard the International Space Station, where the radiation dose is a fraction of what a deep space crew would experience. A crew departing for a 900-day mission carries a pharmacy that must remain effective for the entire duration in an environment that actively degrades its contents. And the psychological impact of a serious medical event aboard a deep space mission compounds the medical challenge itself. When one crew member becomes severely ill or injured, the remaining crew must simultaneously provide care, absorb the workload of the incapacitated member, manage their own emotional response to watching a colleague suffer, in a situation where definitive treatment is impossible, and continue operating the spacecraft without interruption. Grief, fear, and helplessness are not abstractions in this scenario. They are operational hazards that degrade the performance of the people who must keep the mission alive. No spacecraft system operates in isolation. Life support depends on electrical power. Electrical power depends on solar panels or a nuclear generator. Solar panels depend on structural integrity and thermal management to prevent degradation. Thermal management depends on fluid loops, heaters, radiators, and insulation, all of which depend on electrical power to run pumps and controllers. Navigation depends on computers. Computers depend on electrical power and thermal regulation to function within their operating temperature range. Propulsion depends on navigation to know when and how to fire engines. Communication depends on electrical power, antenna pointing, and functioning computers to encode and transmit signals. Every system connects to every other system in a web of mutual dependency. When one system degrades, it stresses the systems connected to it. A thermal control anomaly that causes temperatures to rise inside the crew module increases the power demand on fans and cooling systems. That increased power draw stresses the electrical system, which may already be running near capacity. If the electrical system cannot meet the increased demand, it begins shedding non-essential loads, potentially including scientific instruments, communication amplifiers, or environmental monitoring sensors. The loss of environmental monitoring means the crew has less information about the state of their atmosphere. Less information means slower detection of problems. Slower detection means problems have more time to worsen before anyone notices. To understand how devastating cascading failure becomes when distance removes every external safety net, it is worth reimagining a scenario the world already knows. Apollo 13 is the most famous spacecraft emergency in history, and it is remembered as a triumph of ingenuity and teamwork. On April 13, 1970, an oxygen tank in the service module exploded, crippling the command module's power and life support. The crew survived by using the lunar module as a lifeboat, rationing power and improvising a carbon dioxide scrubber adapter from materials aboard. Mission Control in Houston worked around the clock, devising procedures and relaying them to the crew in near real time. The astronauts splashed down safely 4 days after the explosion. Now transplant that same failure to a Mars transit. 6 months from Earth, the oxygen tank ruptures. The crew loses a significant fraction of their consumable atmosphere and a major power source. But there is no lunar module to use as a lifeboat. The Mars Transit Vehicle is a single, integrated spacecraft. There is no separate, pressurized volume waiting unused with its own oxygen supply and its own power source. Whatever power and atmosphere survived the initial failure is everything the crew has for the remaining months of the mission. And Mission Control cannot help in real time. The signal delay at the time of the failure might be 15 minutes each way, 30 minutes for a round trip. The ground team cannot run a parallel simulation and talk the crew through each step, the way Houston guided the Apollo 13 crew minute by minute. Instead, they must send procedures as messages, wait to hear whether the procedures worked, and send revised procedures if they did not, accepting that every exchange takes at least half an hour. On Apollo 13, the crisis lasted 4 days. The crew was cold, dehydrated, and exhausted, but alive. On a Mars transit, the same category of failure initiates a crisis that must be survived not for 4 days, but for months. Every improvised fix must hold not for hours, but for weeks. Every rationed consumable must stretch not to the next resupply, because there is no resupply, but to the end of the mission. And if the improvised fixes fail, if the rations run short, if a second system failure compounds the first, there is no earth growing larger in the window. There is only the void and the slowly approaching speck of a planet that is still months away. The International Space Station experienced a dramatic example of cascading failure in 1997, when an oxygen-generating canister caught fire in one module. The fire produced thick smoke that filled multiple modules, forcing the crew to don gas masks, and blocked access to one of the two Soyuz escape vehicles. The fire was extinguished within approximately 90 seconds, but the smoke took hours to fully clear. On the station, the crew was in low Earth orbit, with escape vehicles docked and ground support available. In deep space, that same fire would have played out with no escape vehicles, no ground support, and the knowledge that the smoke contaminating the cabin atmosphere cannot be replaced by opening a window. Every molecule of breathable air aboard the spacecraft is a finite, irreplaceable resource. A fire that consumes oxygen and produces carbon monoxide, hydrogen cyanide, and particulate matter does not just threaten the crew directly, it poisons the very atmosphere they depend on. And purifying that atmosphere back to breathable quality requires systems that themselves depend on power, filters, and chemical reagents that may have been damaged or depleted by the fire. And then there is time. A deep space mission to Mars and back using conventional chemical propulsion lasts approximately 900 days, 2.5 years. During that time, every mechanical system aboard the spacecraft is aging. Seals are degrading, lubricants are drying, bearings are wearing. Electronic components are accumulating radiation damage that shifts their operating characteristics. Filters are clogging, pumps are developing play in their rotors. Valves are slowly losing precision. None of these degradation processes announce themselves with alarms. They proceed silently, incrementally, invisibly, measurable only through trend analysis of performance data that the crew must monitor alongside their dozens of other responsibilities. Every engineered system has a mean time between failures, a statistical estimate of how long the system will operate before something goes wrong. For well-designed spacecraft components, these numbers are long. But a 900-day mission contains 21,600 hours. The probability of any single system failing during that time may be low, but the spacecraft contains hundreds of systems. The probability that none of them fail over 21,600 hours is not low. It is vanishingly small. Failure is not a risk to be managed. It is a statistical certainty to be survived. The question is not whether something will break. The question is what will break, when it will break, and whether the crew will have the knowledge, the parts, the tools, and the time to fix it before the consequences cascade into something unsurvivable. The International Space Station receives resupply missions multiple times per year. Cargo spacecraft deliver food, water, spare parts, and replacement hardware on a regular schedule. If a critical component fails, an emergency resupply can be organized within weeks. This logistical lifeline is so fundamental that without it, the station would become uninhabitable within months. A deep space crew carries everything they will need for the entire mission at launch. Nothing can be sent after departure that will arrive in time to matter. A resupply mission to Mars, even if one were launched the moment a problem was identified, would take 6 to 9 months to arrive. If the crew's water recycling system fails on month 3 of a Mars transit, a replacement part launched from Earth on the same day would arrive approximately 6 months later. The crew would have been dead for 5 months by then. Every consumable, every spare, every tool, every medication, every gram of food, and every liter of water must already be aboard. The manifest must anticipate every plausible failure mode and carry sufficient replacements. But spacecraft have mass constraints. Every kilogram of spare parts is a kilogram not devoted to fuel, food, scientific equipment, or crew comfort. Mission planners must make agonizing trade-offs, carrying backups for the most critical systems while accepting the risk that less likely failures will have no spare available. These trade-offs create what engineers call a risk budget. Every mission launches with an accepted probability that certain categories of failure will be unrecoverable. Not because the engineers are careless, but because the mass limitations of spaceflight make it physically impossible to carry redundant backups for every system. A deep space crew launches knowing, whether they think about it consciously or not, that there exists a category of equipment failures for which no repair is possible and no workaround exists. If those failures occur, the mission ends. And in deep space, the mission ending is a euphemism that means the crew does not come home. The spacecraft leaves Earth as a complete system, fully fueled, fully stocked, fully crewed, fully functional. From that moment forward, it only loses. It loses fuel with every course correction. It loses consumables with every breath, every meal, every glass of recycled water. It loses equipment reliability with every thermal cycle, every radiation dose, every hour of operation. It loses crew performance with every sleepless night, every unresolved conflict, every day spent in a confined space with no horizon and no hope of early return. Nothing is added, nothing is replenished, nothing improves. The margin between survival and disaster narrows every single day. And the environment outside the hull, the silent, patient, all-encompassing vacuum of deep space, does not narrow. It remains exactly as hostile on day 900 as it was on day 1. The only thing that changes is the ability of the spacecraft and its crew to withstand it. This asymmetry between an environment that never weakens and a system that never strengthens is the central truth of deep space survival. It is the reason that deep space missions are not simply longer versions of orbital missions. They are a fundamentally different category of endeavor, one in which time itself is the enemy and distance is the locked door that keeps every form of help on the other side. Consider what the spacecraft actually is in functional terms. It is not a vehicle. It is not a habitat. It is a biosphere, a complete, closed, self-sustaining environment that must provide every condition the human body requires to survive. Breathable air at the right pressure, temperature, and composition. Clean water recycled from waste with near-perfect efficiency. Food with adequate nutrition for years of consumption. Protection from radiation, vacuum, thermal extremes, and micrometeorite impacts. A gravitational or mechanical analog sufficient to prevent the worst effects of musculoskeletal and cardiovascular deconditioning. Medical capability ranging from routine care to emergency surgery. Psychological support structures adequate to maintain crew function over years of confinement. And all of this must be powered, maintained, and operated by the same small group of people it is designed to keep alive, using only the resources that were loaded aboard before departure. Earth provides these same services. Earth provides breathable air through a biosphere that has been operating for roughly 3.5 billion years, cycling oxygen and carbon dioxide through photosynthesis and respiration at a scale that involves every forest, every ocean, every microorganism on the planet. Earth provides clean water through a hydrological cycle driven by solar energy and gravity, redistributing approximately 500,000 cubic kilometers per year through evaporation, condensation, and precipitation. Earth provides radiation protection through a magnetosphere generated by a dynamo of molten iron and nickel at the planet's core, a mass comprising roughly a third of the entire planet, spinning and churning to produce a magnetic field that extends tens of thousands of kilometers into space. A deep space spacecraft replaces all of this with a few tons of hardware. The air recycling system replaces the global biosphere. The water recovery system replaces the hydrological cycle. The thermocontrol system replaces the atmosphere's heat distribution. The hull and whatever shielding it carries replace the magnetosphere. Every one of these substitutions is a reduction of many orders of magnitude. The system that maintains your atmosphere on a spacecraft weighs a few hundred kilograms and processes a few cubic meters of air. The system it replaces weighs 5.15 quadrillion metric tons and processes the entire volume of the troposphere. The disparity is not a matter of engineering ambition falling short of the ideal. It is a reflection of the fundamental mismatch between what human biology requires and what a launchable spacecraft can provide. A crew of 4 to 6 people sealed inside a habitat the size of a large bus for 2.5 years faces psychological stresses that no amount of screening, training, or selection can fully mitigate. They are confined in close quarters with the same small group of people, without privacy, without variety, without the sensory richness of a natural environment, without the social support of family and friends, and with the constant background awareness that they are farther from help than any human beings have ever been. Research from analog environments provides sobering data. Studies conducted at Antarctic research stations, where crews overwinter in isolation for months with no possibility of evacuation, consistently document increased rates of depression, irritability, sleep disruption, cognitive decline, and interpersonal conflict as isolation duration increases. The phenomenon is well documented enough to have earned informal names among polar researchers. The winter over syndrome, difficulty concentrating, emotional flatness, and hostility toward crewmates that intensifies during the darkest and most isolated months. Submarine crews, who share many of the confinement and isolation characteristics of a deep space mission, report similar patterns. Extended deployments produce measurable declines in mood, motivation, and cognitive performance, despite the crews being highly trained, carefully selected, and operating within communication range of their command structure. The Mars 500 experiment, conducted in Moscow between 2010 and 2011, simulated a 520-day Mars mission with a 6-person crew sealed inside a ground-based habitat. The study documented significant sleep disruption, with crew members gradually shifting to irregular sleep-wake cycles. Interpersonal dynamics deteriorated as the mission progressed, with increasing social withdrawal and decreasing cooperative behavior. And this was a simulation. The crew knew they were on Earth. They knew that in a genuine emergency, they could exit the habitat. The psychological stresses of a real deep space mission, where the isolation is absolute and the danger is real, would be categorically more severe. Communication delay exacerbates every psychological stressor. On the International Space Station, astronauts can video call their families daily. They can speak with psychologists in real time. They can receive care packages from Earth. These connections to home are not luxuries. They are lifelines. Psychological support is built into the station's operational framework because decades of experience have demonstrated that crew mental health degrades without it. In deep space, a video call to a family member on Earth is not a conversation. It is an exchange of monologues. You record a message and send it. 8 to 24 minutes later, your family receives it. They record a response and send it. 8 to 24 minutes later, you hear it. The spontaneity, the emotional feedback, the comfort of real-time human connection, gone. What remains is a slow, asynchronous exchange that feels more like exchanging letters than talking to the people you love. Over months, this delay erodes the psychological scaffolding that keeps isolated people connected to their identities, their relationships, and their reasons for continuing. And beneath all of these stressors lies a psychological reality that no training protocol can fully address. The knowledge that rescue is impossible. On the station, on a submarine, at an Antarctic base, the crew knows that in a true worst-case scenario, someone will come. It may take time, it may be dangerous, but evacuation is possible. A deep space crew knows that no one is coming. If the mission goes wrong, if the spacecraft suffers a failure beyond their ability to repair, if a medical emergency exceeds the capability of their onboard supplies, there is no rescue ship. There is no emergency return vehicle. There is no abort-to-home option once the spacecraft has committed to its interplanetary trajectory. The crew is alone with their problem. And alone in this context means alone in the most absolute sense the word has ever carried. Surrounded by a vacuum that extends in every direction for millions of kilometers, moving through a void where the nearest human beings who could theoretically help are a minimum of 8 months away, even if they launched immediately. This knowledge does not simply add to the crew's stress. it transforms the texture of every other stressor. A minor equipment malfunction that would be an annoyance on the station becomes a source of existential dread in deep space, because every malfunction carries the unspoken question, is this the one that kills us? A minor interpersonal conflict that would be resolved with a private conversation and a day apart becomes a festering psychological wound when the people involved cannot get away from each other, cannot talk to anyone outside the crew, and know they will be locked in the same confined space for another year. A sleepless night that would be unremarkable on Earth becomes a cognitive performance deficit that might impair the crew member's ability to respond to the next emergency. The psychological literature on extreme isolation suggests that there exists a threshold beyond which human psychological resilience begins to erode, regardless of individual strength, training, or motivation. A deep space mission maximizes every factor that accelerates its approach: confinement, monotony, interpersonal friction, communication delay, loss of autonomy, awareness of danger, and perceived inability to control outcomes, for a duration longer than any previous human isolation experience, in a genuinely life-threatening environment. What this means in practical terms is that the crew's ability to respond to technical emergencies degrades over time. The crew that launches on day one, rested, motivated, mentally sharp, and full of purpose, is not the same crew that faces a critical system failure on day 600. By day 600, they are sleep-deprived, physically deconditioned by microgravity, psychologically strained by confinement and isolation, cognitively dulled by the monotony of the transit phase, and potentially fractured by interpersonal tensions that have had months to compound. And day 600 is when they need to be at their sharpest, because day 600 is when the systems they depend on are also at their most degraded, their most worn. They're most likely to produce the failure that requires a flawless response. This is the tyranny of distance. Not merely that help is far away, not merely that communication is delayed, not merely that resupply is impossible, but that distance transforms the entire mission into a closed system where every resource is finite, every system is aging, every failure is permanent, and the humans responsible for managing all of it are themselves being degraded by the same environment they are trying to survive. There is only one serious attempt in human history to build a completely closed biosphere on Earth, and it failed. Not catastrophically, not immediately, but persistently and instructively, in ways that every deep space mission designer should be required to study. Biosphere 2 was a 3.14-acre sealed habitat constructed in Oracle, Arizona, and occupied by 8 crew members from September 1991 to September 1993. It was designed to be a completely self-sustaining ecological system, containing multiple biomes: a rainforest, an ocean, a desert, a savanna, and agricultural areas. It was sealed from the outside atmosphere, with its own air and water recycling. It was the most ambitious attempt in history to create a miniature version of Earth's biosphere inside an enclosed structure. It failed. Not immediately, not dramatically, but persistently and in ways that could not be engineered away. Oxygen levels declined steadily, dropping from the normal 21% to roughly 14%, equivalent to the concentration at an altitude of over 4,000 meters. The cause was eventually traced to microbes in the enriched soil, consuming oxygen and producing carbon dioxide, which was then absorbed by exposed concrete, removing oxygen from the system without a mechanism to replace it. The crew experienced chronic oxygen deprivation, fatigue, and cognitive impairment. Food production fell short. Pest species proliferated while key pollinators died off. Social tensions became severe, splitting the group into factions that barely spoke to each other. Eventually, additional oxygen was pumped in from outside, which meant the experiment had officially failed its central premise of complete closure. Biosphere 2 had advantages that a deep spacecraft never will. It was located on the surface of Earth, bathed in natural sunlight, surrounded by a breathable atmosphere that could be tapped in an emergency. It had access to gravity. It had access to natural light cycles. It had a land area larger than most spacecraft by a factor of thousands. It was designed and built by experts with unlimited access to materials and construction resources. And it still could not maintain the atmospheric composition, the food production, or the social stability required for 8 people over 2 years. A deep space spacecraft would need to accomplish what Biosphere 2 could not. At a fraction of the scale, with a fraction of the mass, in an environment that is incomparably more hostile, for a comparable or longer duration, with no possibility of outside intervention. The lesson is not that Biosphere 2 was poorly designed. It is that the task of replicating a biosphere inside an enclosed structure is so fundamentally difficult that even the most sophisticated and well-resourced attempt produced a slow-motion failure. The systems that sustain life on Earth are so deeply interconnected, so dependent on feedback loops operating across planetary scales, that miniaturizing them into a closed container produces unforeseen interactions between components that no model had predicted. Consider what Earth actually does for you in a typical second of your life. Right now, Earth's magnetosphere is deflecting billions of charged particles that would otherwise be passing through your cells. The atmosphere above you, weighing approximately 5.15 quadrillion metric tons, is exerting 1 atmosphere of pressure on every square centimeter of your skin, keeping your blood liquid and your lungs inflated. The ozone layer is filtering out ultraviolet wavelengths that would deliver lethal radiation burns within minutes. The mass of the planet beneath your feet is blocking a full hemisphere of cosmic ray exposure, cutting your radiation dose in half. The air around you is 21% oxygen, maintained by a biosphere that has been recycling carbon dioxide and producing oxygen for billions of years. The temperature is regulated by an atmosphere and ocean system so vast that even the most extreme weather events on Earth produce temperature swings trivial compared to the swing between sunlight and shadow in a vacuum. And the gravitational field is pulling on every fluid in your body with exactly the force your cardiovascular system, your skeletal structure, and your muscles evolved to operate under. You do not notice any of this. These protections are so total, so constant, so deeply woven into the background conditions of your existence that they feel like nothing. They feel like the absence of danger rather than the active presence of safety. But they are the most elaborate life support system in the known universe. Powered by a spinning ball of iron generating a magnetic dynamo at its core, wrapped in a 1,000-kilometer thick blanket of gas held in place by gravity, orbiting a stable main sequence star at precisely the right distance to keep water liquid on its surface. Deep space takes all of that away. Not some of it, not the inconvenient parts. All of it. Every layer, every shield, every buffer, every backup, every silent, invisible system that has kept every organism on this planet alive for the last 3.5 billion years. In deep space, you carry your world with you. Or you have no world at all. And the world you carry is a metal cylinder with walls thinner than the floor of your house, powered by solar panels or a nuclear generator, pressurized by tanks of gas that cannot be refilled, cooled and heated by systems that must operate flawlessly for years without maintenance from anyone who is not already trapped inside with you. This is not harder camping. This is not a more challenging version of something humans already do. This is the total removal of the planetary environment that made human existence possible in the first place, replaced by an engineered substitute that is smaller, lighter, more fragile, and more failure-prone by every conceivable measure. There is a photograph taken during the Artemis II mission in April 2026 that deserves more attention than it received. It shows the Earth and Moon together in a single frame, captured through the window of the Orion spacecraft during its outbound trajectory. The Earth is a small, luminous crescent, blue and white, hanging against the blackness. The Moon is larger in the frame, gray and cratered and close. Between them is nothing. Not darkness in the way a room is dark when you turn off the lights. Not emptiness in the way a desert is empty when you scan the horizon. But nothing in the most literal sense the word can carry. No air, no particles, no medium, no substance. Just vacuum extending in every direction, silent and absolute, interrupted only by the two celestial bodies and the thin metal shell of the spacecraft from which the photograph was taken. That photograph captures something that all the data and engineering analysis in the world cannot fully convey. It captures the loneliness of the situation. 4 human beings inside a pressurized capsule no larger than a minivan, surrounded by a void that would kill them in under 2 minutes if the capsule walls ceased to exist. They were at most a few days from home. They were inside a spacecraft designed for short-duration missions. They had continuous communication with Earth. They had abort options. And still, that photograph radiates an isolation so profound that looking at it feels like looking at the definition of vulnerability. Now extend that image. Stretch the distance. Replace the 10-day mission with a 900-day mission. Replace the lunar flyby with a Mars transit. Replace the 1.3-second communication delay with a 20-minute communication delay. Replace the abort to Earth option with no abort option at all. The Artemis program is not a solution to the deep space survival problem. It is the beginning of a conversation with the problem. Artemis II demonstrated that humans can fly beyond low Earth orbit in a modern spacecraft and return safely. Every piece of radiation dosimetry collected by Orion's instruments, every thermal measurement from the spacecraft's hull, every biomedical data point from the crew's health monitoring feeds into the knowledge base that will determine whether a Mars mission can be designed with acceptable risk. But acceptable risk is a phrase that carries different weight when the risk is a 2.5-year mission from which there is no early return. Every engineer involved in deep space mission design knows that the system they are building will not be perfect. Every biologist studying radiation effects knows that the crew will sustain damage that cannot be fully prevented. Every psychologist assessing crew readiness knows that the isolation will exact a toll that cannot be fully predicted. The question is not whether the crew will be harmed. The question is whether the harm can be kept within limits that allow the crew to complete the mission and return alive. And answering that question honestly requires admitting that we are not there yet. The radiation shielding problem requires either a breakthrough in active magnetic shielding or a propulsion system fast enough to dramatically shorten transit times. Neither exists at mission-ready scale. The life support problem requires closed-loop systems with reliability levels never demonstrated for the required duration without resupply. The psychological problem requires either a much shorter mission or advances in crew support technologies that remain in early research. The cascading failure problem requires either extraordinary redundancy, which conflicts with mass constraints, or in-flight manufacturing of replacement parts, a concept being explored through three-dimensional printing but nowhere near operational maturity. Each of these requirements is plausible. None of them is guaranteed, and all of them must be met simultaneously for a deep space mission to succeed. The margin for partial solutions is effectively zero. A spacecraft that solves the radiation problem but not the life support problem still loses its crew. A spacecraft that solves both but fails on psychology still loses its crew. The solution must be total because the environment is total. Deep space does not grade on a curve. Those 4 astronauts floating in their tiny capsule between the Earth and Moon were the most protected human beings who had ever traveled beyond low Earth orbit. They were inside a spacecraft built with 60 years of accumulated knowledge about space environments. They were monitored by thousands of ground personnel. They were on a trajectory designed to bring them home within days. They were shielded by every technology and every protocol that modern space engineering could provide, and they were still, in the most fundamental sense, 4 fragile organisms inside a thin metal shell. Alive only because every system worked, every seal held, every calculation was correct. And the sun did not hurl a killing storm of particles in their direction during the 10 days they were exposed. We understand the problems more clearly than we ever have. But understanding a problem and solving a problem are different things. And the gap between them, in the case of deep space survival, is measured not in years of research, but in fundamental advances across multiple fields that have not yet occurred. Deep space does not hate you. It does not hunt you. It does not conspire against you. It simply exists, with its own physics, its own temperatures, its own radiation environment, its own vast and patient emptiness. And those physics, those temperatures, that radiation, that emptiness happen to be precisely and comprehensively incompatible with the biological requirements of a living human body. You evolved on a planet that spent 4.5 billion years becoming the perfect habitat for your species. Deep space is what exists everywhere that planet does not. It is the default state of the universe, the background condition against which Earth is the exception. And venturing into it means leaving the exception and entering the rule. The rule is vacuum. The rule is radiation. The rule is cold beyond comprehension and heat beyond endurance, separated by nothing more than the angle of a shadow. The rule is silence so complete that no sound will ever reach you from outside your hull. The rule is distance so vast that the light from home takes minutes or hours to arrive, and the nearest help is months or years away. The rule is that nothing out there cares whether you live or die, because caring requires biology, and biology requires a planet. And the nearest planet is a pale dot shrinking in your rear window. Every astronaut who ventures beyond the magnetosphere carries their entire world with them. Their air, their water, their food, their warmth, their pressure, their medicine, their tools, their companions, their sanity. Everything. All of it sealed inside a container smaller than most apartments, thinner walled than most houses, more fragile than most things we trust with our lives on Earth. That container is a masterpiece of engineering. It represents the absolute best that human ingenuity can produce. And it is, compared to the planet it is trying to replace, a candle flame in a hurricane. Not because it is poorly built, but because the task it is being asked to perform, the task of substituting for an entire planet's worth of life support, is so far beyond the scale of any engineering project in human history that even our best efforts produce something that is, by planetary standards, almost incomprehensibly small and almost incomprehensibly fragile. Deep space is not the next frontier, in the way that the American West was a frontier, or the ocean floor was a frontier, or even the moon was a frontier. Those frontiers were hostile, but finite. You could reach them, survive them, return from them, and eventually, in some sense, domesticate them. Deep space is not a place you domesticate. It is a condition you endure, for as long as your artificial world holds together, and not 1 second longer. Every moment of a deep space mission is a moment of active survival, sustained by systems that are always degrading, crewed by humans who are always being worn down, surrounded by an environment that is always exactly as lethal as it was on the first day. There is no moment during a deep space mission when the crew has made it. There is no altitude at which the danger decreases. There is no waypoint past which the remaining journey is easier. This permanence of threat is what distinguishes deep space from every other hostile environment humans have entered. In every previous exploration challenge, the hostility was bounded. The ocean is dangerous, but it contains fish you can eat and wind you can harness. The Arctic is cold, but the air is breathable and the sun returns in spring. The summit of Everest is hypoxic, but you can descend. The desert is waterless, but you can walk toward the horizon and eventually find a river. In every case, the hostile environment contains within itself at least some resources or some path toward safety. Deep space contains neither. There is nothing in the interplanetary void that can be harvested, consumed, or utilized by a human crew. There is no natural shelter, no raw material, no energy source that does not require sophisticated technology to access. The void offers exactly nothing, and it demands that you bring everything. The cumulative weight of these conditions, radiation plus vacuum plus thermal extremes plus distance plus time plus isolation plus system degradation plus human fragility, does not add up in the way individual risks add up in a conventional assessment. These risks are not independent. They interact. Radiation degrades both the crew and their equipment. Equipment degradation increases the likelihood of system failures. System failures increase the physical and psychological burden on the crew. Psychological burden degrades the crew's ability to respond to further failures. Each layer of risk amplifies the others in a feedback loop that tightens as the mission progresses. Deep space does not try to kill you in one obvious way. It erodes every margin you have simultaneously from every direction, on every time scale, through every mechanism, until the artificial bubble keeping you alive can no longer hold. And yet, human beings are going to try. Not because we are unaware of the dangers, not because we are reckless, but because the impulse to explore is woven so deeply into what it means to be this species that no amount of rational risk assessment has ever fully suppressed it. The same biology that makes us fragile in deep space also produced the neocortex that allows us to understand the danger. The engineering capability that allows us to build partial protections against it, and the stubborn, magnificent refusal to accept that any environment is permanently beyond our reach. The real reason no human can survive deep space is not drama. It is not spectacle. It is not one cinematic moment of explosive decompression or flash-frozen astronauts tumbling into the void. The real reason is quieter than that, and more total. It is that deep space removes every condition your body needs to exist and replaces them with nothing. And the artificial substitutes we build to fill that nothing are extraordinary. But they are not Earth. They are not a biosphere. They are not a magnetosphere. They are not an atmosphere. They are machines, built by humans, operated by humans, and subject to every limitation that human engineering and human endurance have ever faced. Consider a thought experiment. Take everything you know about deep space survival, the radiation that passes through walls, the vacuum that kills in 90 seconds, the distance that turns every emergency into a closed-room problem with no outside help, the microgravity that quietly dissolves bone and muscle and vision and immune function over months and years, the thermal swings that stress every material on every surface of the spacecraft, the cascading failures that connect every system to every other system in a web of mutual vulnerability, the psychological erosion of confinement and isolation, and the knowledge that no rescue is coming. Now ask, what would it actually take to solve all of these problems simultaneously? Not sequentially, not one at a time in a controlled laboratory setting with unlimited resources and unlimited time. Simultaneously, in a real spacecraft, with a real crew, for a real mission lasting 900 days, in an environment that detects every solution the moment it is deployed. The radiation problem, solved to current best understanding, would require either a breakthrough in superconducting magnet technology to create an active shield capable of deflecting galactic cosmic rays, or a propulsion system capable of cutting transit times from 9 months to perhaps 6 weeks, a reduction requiring specific impulse values that no current or near-term technology can approach. Either solution represents decades of development from where we stand today. The life support problem requires closed-loop systems for air, water, and potentially food production that can operate continuously for years with zero resupply and near-zero maintenance downtime. No such system has ever been demonstrated in space at any scale. The closest analog, the water and air recycling systems aboard the International Space Station, operate with regular resupply of consumables, regular replacement of components, and regular maintenance support from the ground. They have never been asked to run in complete isolation for years. The psychological problem requires either a mission short enough that human psychological resilience can sustain the crew for its full duration without significant degradation, which points toward the propulsion solution again, or artificial intelligence systems sophisticated enough to provide meaningful social and psychological support to isolated crew members, combined with pharmacological interventions that can maintain mood and cognitive function without producing dependency or side effects that themselves become operational hazards. Neither capability exists in current form. The cascading failure problem requires either a level of redundancy that conflicts with the mass constraints of any realistic spacecraft, since you cannot carry backup systems for every system without making the spacecraft too heavy to launch, or the ability to manufacture replacement components in flight, using additive manufacturing and raw material stocks that themselves require mass to carry. Three-dimensional printing in microgravity is real and advancing rapidly, but the range of components it can produce and the material properties of those components relative to the original parts remain far short of what a full-duration deep space mission would require. And all of these solutions must work simultaneously, without any single point of failure proving fatal, for a duration and in an environment that has never been fully experienced. This is why Artemis II matters, and does not matter at the same time. It matters because it validated hardware. The Orion spacecraft performed as designed. The Space Launch System put the crew on the correct trajectory. The life support systems functioned. The communication systems functioned. The crew returned healthy. Every system check completed successfully represents real data about what works and what needs refinement. That data is genuinely valuable. It does not matter, or rather, it matters in a much more limited way than public coverage suggested, because a 10-day flight to the moon and back is not a test of deep space survival. It is a test of short-duration cislunar capability. The mission never went far enough from Earth for galactic cosmic ray exposure to accumulate significantly. The mission never lasted long enough for microgravity to produce serious physiological effects. The mission never reached a distance at which communication delay became operationally significant. The mission always had an abort to Earth option. None of the hardest problems of deep space were tested, because none of the hardest problems of deep space are present in a 10-day lunar flyby. They are present only when you go further and stay longer. And going further and staying longer is precisely what no crewed spacecraft has ever done, and what no current spacecraft design is capable of doing safely. This gap between what Artemis demonstrated and what Mars requires is not a gap that will be closed by incremental improvements to Orion. It requires capabilities that do not yet exist in propulsion, in radiation protection, in closed-loop life support, in crew health monitoring and intervention, in psychological support, and in the autonomous problem-solving capability of the crew themselves. The Mars mission that eventually launches, if it launches in this century, will look nothing like the spacecraft that flew around the Moon in April 2026. And that is appropriate. The Moon missions of the 1960s looked nothing like the early Mercury flights. The aircraft that crossed the Atlantic in the 1920s looked nothing like the aircraft that first lifted off at Kitty Hawk. The scale of the engineering challenge grows with the ambition of the mission. But the scale of the challenge posed by deep space is not simply a continuation of that growth. It is a step change, a shift in kind, not just in degree. Because the Moon is close enough that every flight to it has been, in the most important sense, close to home. The communication delay is negligible. The return window is days, not months. The radiation exposure is brief. The mission can be designed with generous margins because the penalty for exceeding those margins is survivable. The crew can come home. The mission can be redesigned, and the next attempt can be better. Mars allows none of that. The communication delay eliminates real-time support. The return window eliminates early abort. The mission duration eliminates generous margins for consumables, equipment reliability, and crew health. The radiation environment eliminates the assumption that current shielding approaches are adequate. Everything that made the Moon mission survivable, despite the genuine dangers they involved, is absent from a Mars mission. And everything that makes a Mars mission dangerous is present in full measure for the full duration, with no relief and no recourse. The honest assessment of where humanity stands in relation to deep space survival is this. We understand the problem better than we ever have. We have identified most of the major challenges. We have partial solutions to some of them. We have no solution at all to others. We have never tested any of our solutions in the actual environment they will need to survive. And the environment itself has never offered a practice run. The void is patient. It will be exactly as hostile when we are ready as it is today, and it will be exactly as unforgiving of the first serious mistake. Every astronaut who eventually points a spacecraft toward Mars will carry with them the full weight of what we know and the full uncertainty of what we do not. They will carry their world inside a shell thinner than the walls of a house. moving through an emptiness that stretches for billions of light years in every direction, sustained by systems that must not fail, operated by minds that must not break, for a duration that has never been attempted, toward a destination that has never been reached. It is, without question, the most dangerous thing our species has ever considered doing. It is also, without question, something our species will attempt. Because that is what we are: fragile, ingenious, stubborn, curious, and constitutionally unable to look at a horizon without wondering what lies beyond it, even when what lies beyond it is trying, patiently and comprehensively, to kill us.